Hello and welcome. There is two types of disaster leading to nuclear fallout. A straight-up detonation is the most obvious, and the accidental release. I explore the first one, analyzing trinitite from the 1945 Trinity test. In these two videos, I was able to detect significant amount of plutonium, some upper actinides, and some non-natural isotopic ratio. So in this video, I'll explore the almost 40-year-old Chernobyl disaster using these mushrooms. The 1986 Chernobyl accident has been covered many times in details and was even the story for the mini-series on HBO in 2019. YouTube is full of more or less interesting videos on the tragedy, so I will not add to the chaos. Instead, I'll analyze these penny bun mushrooms collected in the Bryansk region sometimes in 2023. This is an area of Russia a few hundred miles northeast of reactor number 4, and they were sent to me from the Radiacode 103 video, link in the description. To understand why we find what we find in nuclear fallout, it's important to understand the fission product generated in the reactor and the chemistry of these elements. For the most part, a destroyed core releases small particles in smoke and larger chunks of very radioactive material containing the fission product. The uranium-based reactor at Chernobyl used two different types of moderator, graphite and water. This can lead to void of steam and fast neutron, at least for a brief moment during the accident. Fast neutron can fission otherwise fertile isotopes and therefore generate different isotopes and upper actinides usually associated with the nuclear weapon fallout. The actinides and some fission products remain close to the area during release and for the most part stay attached to the larger chunks. Lighter and more volatile isotopes can vaporize and travel further with small particles and smoke. Most of the fission product from the uranium-based reactor are distributed in these two areas of masses around 90 to 100 and about 130 to 150 AMU. In this area, we find cesium-137 and 134, strontium-90, iodine-131, xenon-135 and 133, technetium-99, and so on. All of them have relatively low melting and boiling point, so they will travel with the gases and smoke emanating from the smoldering reactor core. The wind carried them all over the world. They have been detected from Antarctica to Alaska and from the top of Mount Everest to the bottom of the ocean. Of course, over 1,000 atmospheric detonation from the 50s through the 90s add to the total amount of radioisotope found on the surface, but some areas have received more than others. Now, the mode of decay and the half-life of these radioactive elements allows them to be more or less easily detectable. And that's what I'm doing here with these mushrooms. Since they were collected at a distance from Chernobyl, we can eliminate most lanthanide like europium and neodymium, the ruthenium, rhodium, molybdenum, niobium as well, and most actinide like plutonium and americium and higher one like fermium. We are left with the volatile isotopes. We're likely to find significant amount of cesium and barium, some strontium, rubidium, and maybe some zirconium, iodine for sure, xenon, and bromine. Because the accident is already almost 40 years old, we can eliminate the short half-life like iodine, xenon, bromine, and rubidium. What's left is mostly cesium and only the 137 isotope since the 134 has a 2-year half-life. My sodium iodide detector confirmed this selection, and so does a professional high-purity germanium detector. I also looked at the Xray spectrum, and it seems like traces of americium-241 and 243 may be present in very small amount as well. Okay, cool. Gamma spectroscopy detects gamma radiation, but some isotopes are either stable or only emit a discrete electron like strontium-90, or an alpha and a very weak gamma not detected here. To find out, I digested my mushrooms in nitric acid and concentrated hydrogen peroxide, mostly following the EPA method 3050B for soil analysis of metals by ICP-MS, link in the description. I also wanted to compare my results with hopefully clean sample from the grocery store. I am not a hippie or mycologist, but mushrooms seems to have this ability to clean the soil and concentrate heavy metals in their flesh. So you like heavy metal? You must be a fun guy. That's enough. I weighed about 26 grams of dry Chernobyl shrooms, to which I added 120 milliliters of nitric acid and heated to 97 degrees. This may have been a bit too much. When the red fumes finally stops, I let this cool before adding 40 milliliters of 35% hydrogen peroxide, and when the bubbling stops, I evaporate it to dryness. This ugly organic carbon goo was left over. I redissolved this with DI water, centrifuged it, and we are now ready for analysis. The stored mushrooms were first dehydrated at 74 Celsius for an hour and were treated following the exact same process. Since we have a concentrated solution of inorganics, let's first check for gross alpha and beta radiation using the Ludlum 2929. For that, a few drops of this concentrate is evaporated on the dish before counting for 1 minute. After counting the background here, the Chernobyl mushrooms are here. I expected the additional gamma and beta, but there's also a few extra statistical alpha counts. To determine if any actinides are present, I use a triple quad ICP-MS, not unlike this one. I used a 1:10 dilution and a dwell time of 1000 milliseconds for all these isotopes. Despite using clean glassware, uranium was found in both samples in natural uranium concentration for the store-bought mushrooms at 0.68% uranium-235, but 2.3% for Chernobyl ones. Because RBMK reactor uses 2% enriched uranium, some uranium must have been carried to the woods of Russia and deposited in the soil where the mushrooms are growing today. Neptunium-237 could be present as well, but this is a huge could, because the RSD are in the 30s. This means the instrument is not very sure about this detection. Although the counts were very low, plutonium-240 and americium-243 were definitely higher than the blank. And with a lower RSD, both could be considered plausible hits. Californium-249 was also a potential detection, but interference with lead and calcium dismissed this possibility because lead was definitely picked up with all its isotope in matching natural ratio, and calcium is a very likely interference from mushrooms and other natural product. Finally, mercury was definitely present as well at mass 202, but at such a low level, you'd have to eat truckloads of mushrooms every day to barely begin to suffer mercury poisoning after a decade. Before I continue, let me remind you that the beta decay poses a unique challenge in mass spectroscopy, as the mass of cesium-137 is only 0.001173 AMU higher than the mass of barium-137. This is far beyond the mass spectrometer resolution. Are you still with me? We're about to go down a rabbit hole. Because cesium-137 decays into barium-137, I looked at barium-137 and used barium-135 for reference. The idea is to measure the ratio of barium-137 over natural barium to try to determine the age of the cesium-137 contamination. Thinking about the isotopic ratio difference between natural barium and Chernobyl barium, I still try to measure this ratio, assuming all extra barium-137 would be from cesium-137 decay, and I measured a difference of 0.25%, but I quickly realized that nature has a tendency to select some element over others. Calculating the age of the cesium from this assumption yielded an age of 0.7 years. Okay, so I tried my luck with strontium-90 using zirconium-90 as the reference, and this time the age of the disaster is 26 years. Better? Yes, but surprising? Not really. Why? In previous video, I talked about the discrepancy between strontium and barium in seawater, animal bones, lake water, and the environment in general. Despite relatively similar abundance on the Earth, it looks like life, including mushrooms, generally prefers strontium over barium. This has been verified in countless research papers. To complicate things, we know nothing of the mushroom's life story or collection site. The handling could have introduced or removed some isotopes, and this bag could be from different batch of mushrooms collected in different spots, and maybe at different times as well. So is this whole study a waste of time? Yes. I am just an idiot confirming what smarter, richer people have done far better. No, seriously, confirming what others have done is never a waste of time. It helps eliminate conspiracy theories, reinforce our understanding of natural processes. Small details could have been missed, and if you're still watching, you were entertained for 8 minutes and 54 seconds. Constructive criticism is always welcome. So, this is probably not your first YouTube video, and you know what to do. Thumbs up if you like it, subscribe if you want, Patreon, bell, share. I hope to see you again on the next one, and thank you for watching. Damn it!